Okay, so we're back in 4.2 and we're still talking about shifting and stretching of a rational function. And I looked at some of your answers. Some of you had not finished this. So in the chat, can you please tell me what any of these numbers, yeah, it's off now. Thank you. What do any of these numbers do to your graph? Someone says +3 moves 3 left. Exactly. So this guy says, hey, move left. Let me write that down. Move left. Very good. And if you're thinking, Ms. Johnson, why is it moving left? You're like, oh, because it lives in backwards lands. Exactly. Very, very good. So I will take that. And then someone else said the 1 is the vertical shift. In case you don't remember, vertical means up and down, up and down. So now I'm going to move that up 1. Someone else said +3 moves the graph left 3 units. Someone else said the graph is reflected because of the negative. Ooh, who saw that? Who saw that negative and knew that it was a reflection? I got a couple people in the chat. Very good. So if you didn't know, let me just point at everything so that you guys all see. So someone said this guy moves it up 1, up 1. And then this guy over here, this guy makes it reflect. And if you don't know what reflect means, reflect. Hold on a second. Let me just move this closer. So if you don't know what reflection means, it kind of means this. So our normal rational function looks like this: upper right, lower left, right? But that reflection across the x-axis now moves it so that it's, let's do this one. Now moves it so it's like this. Okay. So when I'm graphing this, I'm not going to spend a lot of time on this because my graphing calculator already does it for me. But what I am doing is I'm looking at the trend of that. So I'm going to take this point right here. Let me make him blue. This normal point here of 1, 1 and -1, -1. And I'm going to move it left 3, up 1, and then reflect it. Okay, so the first thing I actually want to do is reflect it. I'm going to make him black. So the very first thing I do is I reflect it. So now those 2 points are reflected. Does everybody see how the blue points got reflected and now they're the black points? Everybody see that? Right? Pretend that I folded it across this x-axis. And then I put the blue point now where the black point goes and the blue point where the black point goes. Very good. So now I'm going to move it left 3. So 1, 2, 3. So I'm going to use a different color, perhaps purple. So now he's here, right? And then moving him up 1 would now be here. You guys all see that? Same thing goes with this guy. I'm going to move him left 3, 1, 2, 3. And then I'm going to move him up 1. Very good. So there, it kind of looks weird, but there are my 2, where my 2 branches will live. Other things that you should have told me is about asymptotes. So someone talked to me about asymptotes. What are some of my asymptotes? I want to make this orange. Where did my asymptotes go? So this was one of my asymptotes right here, right? If you move this thing left 3, where is he now living? 1, 2, 3. Where does he live now? Oh, yeah, x is equal to -3. So I'm going to move all of them and see if there's anything. So once I move him left 3, he's at -3. If I shift him up 1, does anything happen to a line when I shift it up 1? A vertical line, when I shift it up 1, nothing happens to it. So it's still at -3. And if I reflect it down, again, nothing happens to it, right? So my asymptote is at x equals -3. So let me draw a little line in there. I kind of want to do a dotted line here. So 1, 2, 3. So can you pretend that this is a dashed little line? So at x is equal to -3, everyone okay with that? So let me do my other asymptote. What's my horizontal asymptote going to be? So it was here before at y equals to 0. So do your moving and see if anything happens. If I move a horizontal asymptote left 3, does anything happen to it? No, it's just sliding along that line, right? And then if I move it up 1, boom. Okay, now it's at there. And if I reflect it, I'm sorry, you should reflect it first. My bad. You should reflect it first. So reflecting on itself, it's the same thing. Left 3, here it is, and then up 1 here. So here is my asymptote right here. You guys can all see it. It makes sense, right? Because we moved up 1. So let me put this as y equals 1, which makes sense, right? Which makes sense. And then I'm going to draw in my little asymptote here. I wish I was a better drawer. So ignore the blue and black points. And do you see this purple point? And so if I was to draw it in there, and someone asked me this, Ms. Johnson, do you actually want me to graph it? And so, no, I wanted you to sketch it. So the difference between a graph and a sketch is a graph is much more accurate than a sketch. So normally, if you notice, I just like put the little 2 branches in here. So here, I'm just going to pull them in here just so that I can get my branches in. Oh, this is horrible. Ms. Johnson, this is horrible. These are horrible branches, but you guys all see my curves, right? So I would verify it by using my tool. So 1 minus 1 over x plus 3. Is this kind of looking like my purple stuff? No judging, Ms. Johnson, your branches look horrible. Yes, that's correct, right? But it did move over left 3. It did move up 1. I do see this point at negative 2, 0. See this point right here, negative 2, 0? It's this point right here. So those match, right? This other point at, what is that, 4, 2? Looks like 1, 2, 3, 4, 2. Yeah, it looks good. And you can kind of see your asymptotes right here. You guys all see them there, right there. So yeah, this looks really, really good. So remember that it's useless for me to ask you to graph this type of equation on a quiz because you have access to Desmos. That's a useless question for me. I do ask you questions like this. Find all the features of this rational function in order to help you describe the graph of this. So that's like you saying move left, move up, reflect it. The branches are, let's see, lower right, upper left. Here's a couple points. Do I actually want you to like graph it and use accurate points? No, because look, Miss Johnson can't even do it. It looks like a big old mess. But I should be able to pull things off of here. Like, oh, I see her asymptote. I see her whatever. The other things that I would also encourage you to find are your intercepts. Okay. Sometimes your intercepts are going to be easy to find and sometimes they're not. If they're easy to find, great. If not, then don't. The y-intercept is going to be easy because I'm just going to plug in 0. So I get 1 minus 1/3. So that's 2/3. That's supposed to look like 2/3. That looks more like 2/3 right there, doesn't it? Yeah, that looks more like 2/3. Hold on, let me try to get better. Yeah, there it is. Right. Your x-intercept is right there. We found it because of the shifts. So does anybody have any questions on when I'm graphing stuff like this? Any questions? Things that should pop out to your brain super quick are these movements. What we've been doing this since, I don't even know, the beginning of the year. The movement should pop out to you. The reflection is technically new. And some of my students get backwards on, Ms. Johnson, when do I reflect? Should I reflect first? Should I reflect last? So I'm not going to tell you when to do it just because I want you to kind of figure that out. Sorry, that's kind of my way of teaching. But one of the ways that you could definitely check is by plugging in points and making sure your branches are in the place that you did, right? Okay, so very good. I'm going to go over this last one and then we're going to go over takeaways. This one really quick. Let me see. Can we label off? Let me see really quickly. All these numbers here, you could tell me the exact same thing that you said before. You would say something like shift right 4, shift down 2. This one doesn't have a reflection. What does this 3 do to everything? What does this 3 do to everything? Yeah, it's called a stretch, right? It's a multiplier. It's a multiplier. So it will change a couple different things. Okay. So when I'm graphing this, let's put this out there. When I'm graphing this and I have my axes and I have my axes, right? And then I have my movements of right 4, down 2, right? So then that tells me my asymptotes are going to be moved and so on and so forth. That 3 doesn't affect your asymptotes, right? That 3 actually affects these little points right here. This point here may not look like it's there anymore, right? So what is, like, Ms. Johnson, what do you mean? So normally when I have my points, and I'll put it here, right? Normally I have it, now this is not reflected. So it's up here and down here, right? So think about this movement, right? So I'm going to move it. I don't know, I'll use this to show you. It's, you told me move right 4 down 2. So move right 4, boop, down 2, boop. So Ms. Johnson, are you saying this point is not going to be there? Oops, let me go here. Is this point not going to be here anymore? So let me move right 4, 1, 2, 3, 4, down 2 here. Is this point not going to be here? That's your job to check it. So according to this, I should be plugging in 1, 2, 3, 4, 5. I'm going to plug in 5. And then without me stretching it, it's at -1. I wonder what it'll be now, right? Now I'm not going to use this calculator to graph this. I'm going to use this calculator to solve the idea of what's happening. So I'm going to put 5 in there minus 4. Is that how I want to see it? -2 plus 3, 5 minus 4, and it's 1. Wait a second, Miss Johnson. I thought you said that it was down 2. Why is it now up 1? Like, what happened? Wait, let me make sure that I did this right. 5 minus 4, 1, 2, 3, 4, 5. Yeah. So Miss Johnson, why did it end up here? That's the point, right? You're figuring out why that stretch, how this moved all of these points, right? So if you think about your asymptotes, for example, your asymptotes, let's see, should be x is equal to 4 and y is equal to -2, right? So let's draw those in and see if that helps you understand. I like dashed lines for asymptotes in case you didn't know. So what did I say? X equals to 4, so dash, and y equals -2. And you're saying, Miss Johnson, this point is right here. It's going to be right here after I stretch it. Yeah. So can you imagine me stretching something? Like pretend you had a rubber band and you're stretching it, right? This point got stretched away from my asymptote, away from my asymptote, and now he's here. I wonder what happens with this guy. I wonder what would happen. Do you think he would go up or do you think he would go down? If I stretched it, do you think this point that should be here before the stretching, should he go here or should he go here or should he go up here? Where do you think, up or down? And then I'm going to just plug in to check. What do you guys think, up or down? Well, let's see. So I plugged in 3. I got -5. Oh man, he's all the way down here. 4, 5 right here. He's all the way over here now. So do you see how my branches got a little bit more stretched than before? Yeah, that's okay. I'd rather you make mistakes here. Yeah, awesome. Make your mistakes here. Who cares? No one saw that. Only me. Okay, so here goes. This is where the curve would go, right? Something like, I don't know, something like this. Hey, that looks way better than before, huh, guys? Johnson, she's getting better at drawing, right? So there's your curves. That's where I think it should be. And then actually now let's just graph it. Look, that's where it is. And some of you would say, Miss Johnson, I don't see the stretch. Now you don't see the stretch because you're not comparing it to not this. So what I'm going to do is I'm going to show you comparing your stretches so you guys can see both of them. Now, if I want to compare a stretch, I'm going to put this number back to 1. Do you see the difference between the blue function, which is not stretched, and the red function, which is stretched? And you're like, slightly. But over here, Miss Johnson, it looks the same. Yeah, down here, it looks the same. But right in here, it's being stretched. Can you think about it being stretched away from like where your axes intersect. Do you see how they're like being kind of like pulled away? That's what I think about. That makes sense? All right. So that's a little bit more on stretching. And so now we're going to go into takeaways. Now, some of you are really strong in looking at these numbers and being like, boom, this is what it does. This is what it does. And so your idea here is kind of like how when you first started learning how to read, right? And I've told you this example before. So before you did not know that this word actually meant cat, right? And so some of the books that your mom or dad or whoever got you, and then they drew, oh my gosh, this is Miss Johnson trying to draw a little cat here. Oh my gosh, this is horrible. This is a tiny version of a cat. Pretend that looks like a cat. Okay, just pretend. Right? Haha, just kidding. So they put a little picture of a cat here. So your brain would recognize, oh, that is a cat. Oh, that must mean that word is cat, right? So right now you are getting used to understanding what each of these quote unquote letters, right? Each of these numbers do to your function. Eventually you should get to the point where you should be able to picture what is happening to this, right? All right, moving on, let's go to takeaways. So our takeaways work like this, right? This is what you should have learned in this whole lesson. Now, if you got most of this, awesome. If you got some of this, awesome. If you got none of it, you have work to do. If you got all of it, even better. I don't expect that everyone should have gotten all of it on the first try. Now, after you do your practice problems, then it should be like, oh, I kind of get it, right? So let's go over this just so that we're all on the same page and everybody understands what we were going for. Okay. So it says identify the transformation in the equation f of x, so k plus b over x minus h. You should have learned that the vertical shift was k. A lot of you got that. You should have learned that the horizontal shift is h, right? For x minus h, remember backwards land. Minus h makes you think of going left, right? But remember, x lives in backwards land. What you think is right is really left, and what you think is left is really right. So left for x plus h. Vertical stretch factor of b, remember this guy right here, and you understand what it's stretching. It's stretching away from kind of like your intersection of your asymptotes. And then reflection if the function is negative or b is negative. So someone pointed out really quickly, like, hey, Ms. Johnson, that plus is a minus. That means there's a reflection. Awesome observation. Now you guys have much better eyes than I do. So you should be able to pick these things out, right? You should be able to say, you're my vertical stretch. You determine, you and you together kind of determine if I am reflected, right? This is a stretch. This is my horizontal shift, right? So that's really what we're doing here. Now, if you're I will say, if you're so dependent on the calculator that you have to use the calculator to figure that out, hey, that's just kind of where you are right now. Your goal is to get to knowing and naming what each of their jobs are, because each of them have a job, right? Mark the asymptotes. So your vertical asymptote is always going to be at x is equal to h. So going back here, that guy tells me my vertical asymptote. This guy tells me my horizontal asymptote, right? Some of you knew that. It says find the anchor points, right? So my anchor points are always going to sit to the right and to the left of my vertical asymptote. So here they're giving you some like very specific things. I don't do well with things like this, like formulas, right? So I want to say, if you want to memorize this, great. If you want to look these up during your quiz, great. But I'd rather you just kind of understand if you have a vertical asymptote. So like this, notice we were looking at the people to the one to the right and one to the left of your vertical asymptote, because that's going to tell you where what they are calling anchor points are. So once we plug those in, then we figured out, oh, that's where the branches is, and that's where the other branch is. Okay. So Miss Johnson, I'm not going to ask you a question. Okay, is it right? One up B? Like, are you going to do this? Like, no, I'm just going to ask where it makes sense. So, but if you did do this, you could figure out where those are. So let's just look at this one, right one up B. Okay. So, let's see, where's it's this guy. So right one from the intersection of the asymptotes, you're going to go right 1 and you're going to go up B. And this is our B. So you're going to go up 3. 1, 2, 3. Now you can memorize that formula, or you can do like Ms. Johnson does and just plug in. Okay. I'm more of the believer of what works all the time and not just for this case. Okay. So count the opposite anchor points on the opposite side. And here they're talking about your symmetry. So if it's symmetrical, then you can go up 1, right 1 up 3, or left 1 down 3, because it's symmetrical. That's what they're saying there. And if there's a reflection, don't forget that the branch is flipped, right? All right, last but not least, here's try one more. You should be able to pick off why your vertical asymptote is here, why your horizontal asymptote is here, what made it go flipped, and what made this point not live right here, but right here. So these are questions that I would be asking you. A classic question would be like this. Write the equation of this function. And because you understand how to find the asymptotes, how to find anchor points, how to check your anchor points for any stretching, you could write this equation. It's just going backwards, right? Pretty classic in math for you to go forwards, and then for them to expect you to go backwards. Okay. So the problem with you depending on the calculator so much, you can't say to the calculator, hey calculator, look at this problem and give me the graph. Guess what graphing calculators can't do? They can't go backwards. You can't say, okay, here's the graph, I want the equation. Calculators can't do that, because a graphing calculator can graph. It can't go backwards. Does that make sense? All right, that's your job as a human. So hopefully right now, you should be able to look at every single one of these like symbols, these numbers, these everything, and make sure that it's it. Yeah, someone said I could just keep putting numbers in until I get the equation. And that's kind of true. But even you putting numbers in, you have to know a little bit about like your vertical asymptotes, because you can't just go like, okay, I think it's 1 over X. Oh no, that's wrong. And then, I mean, maybe you know enough to be like, oh, that's flipped, so that means it has to be negative. Something like this, right? Okay, I got it right. Now I need it to move up 2, but up 2, do you know where that plus 2 needs to go? Like, is it next to X? Is outside? So there is some, you're making your world a lot easier by knowing what each of those numbers do, for sure. All right, really good job. Thank you for listening.